what's happening here? Playground current. Yeah, so there are two people here. So did both of you attend the other classes as well? The other TA's lectures as well? Yeah, it's just because it's gonna be a bit repetitive, the lecture. Yeah, I prepared the exact same thing that they showed you, but yeah, I'll still anyway start. Yeah, I hope my screen is visible. Okay, anyway, so far we saw the relationship between like one variable and the outcome of one given variable. So we had the random variable, random variable in your x-axis and the probability function in your y-axis. So we just had like one input and one probability outcome. But now in this week's lecture, what was focused on was bivariate joint probability distribution. So this means that we have two variables that give us one outcome. So like we here, let's consider like a three-dimensional thing, x, y, and z. We have random variable x, random variable y, and in your z-axis, in your other third dimension, you have your probability function. So it's similar to like having a square and calculating the area of a square, whereas having a cube and calculating the area of a cube. Like there's length, breadth, and height, like a rectangle. If you consider in your two-dimensional aspect, you'll just have length into breadth. But whereas three dimensions, you'll have length, breadth, height. So it's just something similar to that. And like one example could be like, so your disease outcome. You have, let's say somebody has a disease, and the outcome of the disease would be dependent on many variables like the age, the what do we say? Uh, Age could be a factor, the symptoms, the severity of the disease, and whether the person is vaccinated, whether the person is immunized to the disease, or whether he has previous exposure to the disease. So these are all several random variables that contribute to one outcome, which is the disease. But in this case, we're just looking at bivariate, where so bivariate is a case where two such variables contribute to an outcome. So yeah, that's the gist of this. So when we talk about, so when we have these two variables, looking at one variable, it gives us a marginal probability, which tells us the probability of like one of these variables, and a joint probability considering both variables. So let's look more into detail about these. And yeah, so even in this case, we'll have PDF and CDF, PDF or PMF in case of continuous random variables, and in case of discrete random variables. You'll have like a PMF and you'll have the corresponding CDF function. So yeah, the problem for discrete random variables, let's first look at discrete random variables now. So the probability could be denoted by this. So these are like point probabilities. The probability, the joint probability of x and y, where x is equal to a given value of I and y is equal to a given value of j. So yeah, the number of observations of I need not be equal to the number of observations in j. So yeah, this is one thing to note. And also like what you do in a joint CDF is, yeah, you consider, so x and y, each of these, they have two ranges. So x is in a given range. It could be anything between like minus infinity to plus infinity, and y could also be anything between minus infinity to plus infinity. So what you do is you take a double integration of both x and y, both the probability functions of x and y. That's what is given here. This is your inner integral. You integrate this, you get some value here, some expression here, and then you again integrate this with your outer integral. Yeah, so the order of this doesn't matter. You can first integrate in terms of dx, in terms of x, or you could first integrate in terms of dy. But in some cases it might matter, but yeah, the examples that we're looking at, it won't be an issue. So either way you do it, you'll get the same answer. And also it also follows independence. Such random variables, they also follow independence. Like if you remember, we saw, like if you let's say you have two events A and B. These two events are considered independent if the probability of A intersection B is equal to the product of the probabilities, is equal to product of probability of A into probability of B. So if you had this, you can say that the A and B are independent events. So similarly here in this case, yeah, so if X and Y are independent, the joint probabilities, the PMF of the joint probability is just equal to the product of like each of these probabilities. And its CDF is also given by this function. So yeah, let's first look at marginal probabilities and conditional probabilities for discrete random variables. Like just to brief about that a bit before we get into this, I can just how do I add a new slide? New slide, yeah. So let's just say we have a class of students. We say we have girls and boys. So this is just like some example, random example that I've chosen. And we have, so there are several subjects, maths, physics, biology. So let's say 10 girls take maths, 15 girls take physics, and 20 girls take biology. And so, and like in case of boys, 15 take maths, 10 take physics, 25 take biology. So what would be the sum of all these? 20, 15, 30, 45. And 25 plus 35 plus 15 is 50, right? And then 25, 25 again. What is it? 575. So yeah, so this is X, Y, let's say. So if you want to see the marginal probability, it's 45 in this case. So what you do is so let's say this is Y. Like this is a variable X, this is Xi, this is X, uh, this is X1, this is X2, this is Y1, Y2, Y3. So all these are Y, all these are X. So when you want to find the probability of girls, you sum up all these. You sum up all the girls who have taken maths, all the girls who have taken physics, all the girls who have taken biology. So it's something similar to this, what we're going to see. And when you want to see like all the students who have taken maths, you sum up both girls and boys. So this is the marginal probability for this particular value. So yeah, so we'll look at a similar concept to this. We will look more into detail. So it's given by the notation like P of X. So this is your PMF. P of X is equal to Xi. P of X, like it's just a summation of the joint probability Pij over the range of all the values of Y. And if you want to find out P of Y, the marginal probability of Y, you sum up the expression of the joint probability over all the values of X. So we could look at this like this simple example here. So what is given here is your joint probability. Your joint probability is given by X plus Y by 21. And the given values of X are 1, 2, 3 and Y is 1 and 2. So if you want to find the marginal probability of X, you have to sum up, you have to apply all the values of Y to this expression and sum it up. So it would just be X plus Y is equal to 1 divided by 21 plus X plus Y is equal to 2 divided by 21. So this would give you, so x plus x, 2x, 2 plus 1, 3, 2x plus 3 divided by 21. So this is your marginal probability of x. P of x is this. And similarly, you can do the same thing for the marginal probability of y. You just apply all these value of x in this expression. So it would be 1 plus y divided by 21 plus 2 plus y divided by 21 plus 3 plus y divided by 21. So if you substitute all this, you have 3 plus 2, 5, 5 plus 1, 6 plus, there are 3, y plus y plus y is 3y divided by 21. So this is your marginal probability of y. This is your marginal probability of x. So now the next thing here is conditional probability. Conditional probability. So if you remember, we saw that conditional probability, what you would do is you would do P of A intersection B divided, if you want like P of A given B, you would write this. P of A intersection B divided by P of B. So this is similar here. So let's say you have P of X given y is equal to a specific value. So what you do is you just do the joint probability Pij, joint probability divided by marginal probability of y. So whatever is in the denominator here, you take the marginal probability of that would be in the denominator here. And similarly, if for P of y given x, so here you fix a specific value of x and you want to derive an expression of the probability of y given that specific value of x, you just do the joint probability divided by marginal probability of x. So let's solve this here. Just a second. Okay. I'm in question number 8. The answer was not there in the options. Okay. Yeah, I was just reading the chat box. So question week 7, question 8, the option was not there. So yeah, this concern was already raised. And your marks have not been detected, but your marks will be changed later on. Yeah, like they'll be changed. So that's still under process. The marks haven't been updated yet. So yeah, this has been notified, and yeah, the marks will be changed. Okay, anyway, let's continue, get back to this. So yeah, we have calculated the marginal probabilities. Now we want to calculate the conditional probability for x given y. Now what do we do in this case? So we just do Pxy joint probability divided by the marginal probability of y. So what is this? The joint probability is given in the question. X plus y divided by 21 divided by the marginal probability of y we calculated here in this expression. 6 plus 3y divided by 21. So 21 get cancelled. So this would be x plus y divided by 6 plus 3y. So this is your joint probability P of x given y. And then similarly, P of y given x would be x plus y divided by 21 divided by this marginal probability of x. 2x plus 3 divided by 21. So cancelling it, x plus y divided by 2x plus 3. So now we know for discrete random variables how we calculate the marginal probabilities and how we calculate the conditional probabilities. And so yeah, so we have seen before about expectations. So expectation, you basically sum up the given value. Like for example, roll of a dice. So what do? You do 1 into 1 by 6 plus 2 into 1 by 6 plus 3 into 1 by 6 and so on. So you basically sum up the outcome, the random variable, the number, multiplied by the probability of getting that outcome. So the same concept is applied here. So yeah, let's look at this simple derivation. And we just calculated that the marginal probability of x and y, we calculated here from this previous slide. Yeah, so 2x plus 3 divided by 21. And marginal probability of y would be 6 plus 3y. 6 plus 3y by 21. And similarly, joint probability of x given y is x plus y divided by 6 plus 3y. Right? So now how do you calculate the expectation of x? So if you want to calculate the expectation of x, you just have to apply this directly here. Sorry, here. Like you have to apply the value, sum up the values of x to the marginal probability of x. So what you do here is 2x. So x is 1. 2x. So basically you substitute this here. So x is 1. 2 plus 3 by 21. Sorry. So you have to do this like 1 into 2x, 2x plus 3 by 21 plus 2 into 2x. Now x is equal to 2. So 2 2s are 4 plus 3 by 21 plus 3 into 2 3s are 6 plus 3. 6 plus 3 by 21. So solving this, you would have 2 3s are 6. No, sorry, 2 plus 3. 2 plus 3, 5 by 21 plus 4 plus 3, 7. 7 2s. Yeah, 4 plus 3, 7. 4 plus 3, 7. 7 into 2, 14 by 21 plus 6 plus 3, 9. 9 3s are 27 by 21. So your answer would be 19 plus 27, 46 by 21. So this is your E of x. Right? You just directly substitute the values of x, the value of each value of x multiplied by the marginal probability of x. And now for conditional probability, E of x given y is equal to 2. So for y, the value of y is fixed. So you just substitute it here. So x plus 2, y2 is given, x plus 2 divided by 6 plus 3 2s are 6, so 6 plus 6 would be 12. So x plus 2 by 12. And you do the same thing now here. Yeah, so what do? You just need to do the same thing. So 1 into 2 plus 1, 3, 3 by 12 plus 2 into 2 plus 2, 4 by 12 plus 3 into 3 plus 2, 5 by 12. So if you substitute this, you would get 3 by 12 plus 4 to 8 by 12, 15. So you'd get 26 by 12, which is equal to 13 by 6. So yeah. So this gives you an idea of how you calculate expectation of x and the expectation of x given y. So you just substitute each of these values with the, like for E of x, you just substitute it to the marginal probability. And for E of x given y, you substitute it to the conditional probability. Yeah, this is a simple example here. And now we saw discrete random variables so far. And now we look at continuous random variables. So continuous random variables, it's like instead of summation, we just do an integration. You calculate the area under the curve here, right? So if you want to calculate the marginal probability for x, you differentiate, you integrate the joint distribution function in terms of y. So the limit would be all the values that y can take. It's not minus, it's any value that y could take. It could either be 0 to y, or it could be minus in any minus number to y, or it could be like y to 1, and it could be anything. So if you want to calculate f of x like fx of x, you just integrate the joint probability over a limit with values of all the values that y can take. And if you the same thing you can do with the marginal probability of y. You integrate this function over all the values x can take, dx. So it's just you have to be mindful of this. So f of x, you integrate in terms of dy and dx here. And here, so you have the corresponding CDF as well. So yeah, you integrate whatever value you get here, you integrate this over all the values of x. And for y, you do all the values of y. So for continuous random variable, so for PDF, what you do is marginal probability of x, you integrate in terms of dy, right? Marginal probability of y, you integrate in terms of dx. But for CDF, for f of x, this one, you integrate the PDF, the marginal probability of x in terms of x, and for f of y, you integrate it in terms of y. So these are just some things you need to remember. And similarly, you have the conditional probability as well. So it's basically your joint distribution divided by your marginal probability. So it's the exact same thing. So here's an example. You have the joint distribution function. This is wrong here. So f of x, y, x comma y, the function of this is 2. So this, and your given limits are 0 less than equal to x less than y less than 1. So you'll understand this if you draw a straight line. So this straight line is basically tells us x is equal to y. So in that case, like if you have 1 here, you'll also have 1 here. If you have 2 in your x-axis, this point will also be 2 in your y-axis. And 3, 3. So now they say y is greater than x. So this denotes that the upper area, the area of this upper region. Y greater than x denotes that, because if you look at a point here, your x is equal to 2, but y is something less than 1. So y is equal to 1 if you look at this point here. So here y is less than x, but in the question, y is greater than x here. So yeah, it has to be above this line. Like if you just consider this region here, your x is equal to 2 and y is equal to 3. So 3 is greater than 2, so it's satisfied here. So yeah, this is how you just graphically represent this. And yeah, let's calculate the marginal probability function for f of x. So basically, you do an integral, you write the function, and you do it in terms of dy. So now what are the limits that y could take? So the lower limit for y is x, the upper limit for y is 1. So if you write that here, like if you solve this, 2 is a constant, and this would dy, if you integrate dy, you'll just have y, 1x. So applying these values, your upper limit is 1, 2 into 1 minus your lower limit is x. So this is your marginal probability for x. And similarly for y, you write the function, integrate in terms of x. So x can take a value of 0 to y. Lower limit is 0, upper limit is y. You do that here. So this would be equal to 2x 0 to y. And substituting this, you'll have 2y minus 2 into 0, 0. So you'll have 2y. So now you have the marginal probabilities. Now let's say you wanna, they've given the value for this points here. They've given the value. So what do you do here? So you just integrate this. You have like for x, you do dy. Oh, sorry, this is your CDF function where x is equal to 0.5. So what do you do here? You have the PDF of x, which is 2 into 1 minus x. So you integrate this in terms of x. And the limits that x can take is 0 to y. But yeah, the upper limit for x they've given the question here is 0.5. So that's how you decide the limit here. And now solving this, you can split this into 2. So the 2 is a constant, 0 to 0.5 dx minus, again, like 2 is a common constant, and you have x dx, 0 to 0.5. And yeah, if you solve this further, you'll have 2 dx is, like if you integrate it, you'll have x 0.50 minus 2, and if you integrate x, you'll have x squared by 2. So again, x squared divided by 2 is a constant, so you just keep it out, you cancel these, 0 to 0.5. So now substituting this, you'll have 2 into 0.5. 2 into 0.5 is basically a 1 minus x square. So 0.5 square minus 0 square. So 0.5 square is 0.25. So you'll have 1 minus 0.25. So your answer for this is 0.75. And similarly, you can do the same thing for y. Do you want me to calculate that? Or is it okay? Anybody? Is that okay or should I?
Madam, calculate.
Okay, sure. Hmm. What do we have here? Fy. So yeah, from current slide. So we had f of y is equal to 0.75. So now what will you do here? You have to apply the PDF of f that y that we derived. So 2y dy. And what are the values that y could take? So we had an expression 0, x, y, 1. So now what are the values that y could take? It could take x to 1. But yeah, so y could just be like 0. So this lower limit would be 0.7 here. This will be 1. Now 2 is a constant. And if you integrate y, what will you get? Y square by 2, which comes out 0.751. So 111 minus 0.75 the whole square. So if you just solve this, you'll get the answer. And yeah, now next, joint probabilities. So, sorry, conditional. Conditional probabilities, we had f of x given y is equal to y. X given y is equal to y. So this can be given as, so the question, the joint probability was 2. So this is your joint probability, that is 2. Divided by, what is the marginal probability of y? We calculated it here, 2y, right? The marginal probability of y here is 2y. So we write 2y, we cancel these, 1 by y. And similarly, f of y given x is equal to x, y given x is equal to x. Your joint probability is 2 divided by marginal probability of x was 2 into 1 minus x. 2 cancel. So you'll have 1 by 1 minus x. So yeah, that's it. This is how you calculate these. And now similarly, like you had the conditional probabilities for these bivariate distributions, you similarly have expectations as well. So expectation, let's just see how you calculate these. So yeah, the expression is the same thing. The any value that the random variable could take. So the random variable could be one value, or it could be a function of both x and y. So that's what this g of x comma y means. And so this is your uh, CDF, the probability function of it. The conditional probability function of it, sorry. Yeah, so this is your CDF, conditional probability. And yeah, let's see an example. If the question is this, yeah, you just have to solve these two. So expectation of x given y would be, yeah, so let's consider the same question here. So we have to do this. We have to just apply these to the formula. So yeah, let's do this first. You have x and your f of x given y. What was your x given y? It was 1 by y, right? So into 1 by y dx. Again, what are the limits these could take? So dx, x takes a limit 0 to y. So because you're doing this in terms of dx, this y, any term that has a y is a constant. So you bring this out of your equation. And when you integrate x, you'll have x square by 2, 0 to y. And now what happens? You still have 1 by y square. You bring this 2 outside, right? 1 by 2y, and you have y square minus 0. So basically you have y gets cancelled, you have y by 2. So this is your conditional expectation of x given y is equal to y. And now similarly, expectation of y given x, you have y, and the value for this f of y given x was 1 by 1 minus x. And dy, y could take the values x to 1, x to 1. Now, because you're doing it in terms of y, this term becomes a constant. You bring it out of your integral, x1 y dy. So you will have 1 by 1 minus x. Y is y square by 2. 2 also we keep it outside. Y square by 2. 2 is a constant. We keep it out here. And limits are x to 1. Now we substitute these. 1 by 2 into 1 minus x. 1 minus lower limit x square. So this 1 minus x square is basically in the format like 1 square minus x square. It's actually a square minus b square. So like we have learned in algebra, a square minus b square can be written as a plus b into a minus b. So we do the same thing here. You write a plus b, a minus b. So a is 1, b is x. So you write a plus b, a minus b divided by 2 into 1 minus x. So these two get cancelled out. And your final value is 1 plus x by 2. This is your final value. Yeah, that's it. So we have calculated the expectation of y given x as well. And now we are coming to the last topic that was discussed. Yeah, the other section, the last section. We have covariance. So what do you mean by variance? We know that variance is basically you have a mean and the deviation from your mean is basically variance. So all these points are x. So your mean is x bar. So this is x1, x2, x3, and so on. So variance for each point, like it's given by a summation of x minus x bar. Like, yeah, let's just look at that. So you can write it in terms of this way, in terms of expectation, and you can write it using this relation as well. So yeah, let's first look at this. So you write expectation of, so because we have two variables here, you like for x, you do x minus mean of x. So mean of x is again expectation of x. You have that multiplied by y minus mean of y, expectation of y. So you take the expectation of this whole thing. And yeah, you just, now you solve for this x into y, xy minus expectation of x into y is minus exy. So you just basically multiply all these terms and you expand the equation like this. And yeah, you just rewrite these. And finally, if you solve this, you'll get some expression like this. E of expectation of xy, which is the joint expectation, minus expectation of x into expectation of y. So when you say variance of x, it basically means covariance of x comma x. So yeah, think about it. Like instead of y here, if you substitute x in all this equation, what will you get? Like let's just consider this last bit. You write, instead of y, you write x. So you'll have e of x square minus so you'll have e of x the whole square. So yeah, if you remember in the previous lectures, the variance of x was given by e of x square minus e of x the whole square, right? So yeah, that's what it says. So that's when you do covariance of x comma x. This is what you get. So when you do x comma y, you have this expression. So it can also be written in this way. So it's basically the summation of all points, like for each point at x minus the mean of x into y minus the mean of y. So you add all these values at each point divided by the total number of observations, which is n. So here because we want to keep simple mathematical terms, we consider the sample size as your population size. So that's why you have n. But what R does is, it calculates this term. It calculates your summation I is equal to 1 to n, xi minus x into yi minus y mu. It calculates this divided for n minus 1 observations. So when you do covariance of x minus y in R, it'll give you some number, but that number is equal to this expression. So when you want to calculate it like this, what you have to do, so let's say R gives you 0.2 and your sample size is let's just say 11. So what you have to do is uh, wait, let me put it a different way. You have this observation like xy, all that summation divided by n minus 1. This is what R gives you. You want to write it in terms of n. So you just multiply n minus 1 divided by n. So let's say R gives you this value of 0.2 and your n is 11. So what will you do? You have to do 0.2 into 11 minus 1 is 10 divided by 11. So your final answer would be 2 divided by 11. So yeah, whenever you have assignment problems, you have to, like when you do it with R, you should not just write the answer, what you get from R as your final answer. You have to multiply it into n minus 1 divided by n because of this. Okay. Yeah. Similarly, yeah, like if x and y are independent, the joint expectation would be equal to the product of expectation of x and expectation of y. And one more thing is, let me just add another slide. So yeah, covariance, it could be either positive. You assume that X and Y have a linear relationship. So your covariance value could be either 0, which means there is no relationship between X and Y. So X and Y are independent. Covariance XY is equal to 0. So if your covariance is positive, there is a positive linear relationship between X and Y. And it could also have a negative relationship, like Y could be inversely proportional to X. Like as X increases, Y would decrease. So it could have an opposite trend as well. So covariance just tells us about this, the direction of the relationship, whether it's like positive, negative, or no relationship. So whereas correlation, on the other hand, it tells us which direction the relationship is. It tells us whether it's positively correlated or negatively correlated. And also it tells us how strongly they are correlated. So on a scale of 0 to 1, if you have 0.9 correlation coefficient, so in R, correlation coefficient is denoted by R, capital R. So capital R means correlation coefficient. So if R is 0.9, it means that it's a almost linear relationship. So a perfect linear relationship would have correlation coefficient is equal to 1. So yeah, if you get anything close to 1, it's good. Or if you have a correlation coefficient of 0.2, it means a very weak correlation. And yeah, you could also have -1, which means a perfect negative correlation. Yeah, so correlation basically tells you both direction and magnitude, whereas covariance tells us only about the direction. So yeah, this was something that was introduced. You build a covariance matrix, but these will be discussed in detail in your next week, I guess, about what this covariance matrix means. But yeah, to be able to solve this week's lectures, it's enough if you know these. So covariance of x comma x is basically variance of x, which we just discussed here. And if you have like constant terms, like covariance of ax plus b, you just bring out these constant terms and multiply them. So yeah, this plus b and plus d, it's fine. Like it just adds something to your final output. But this basically adds some weightage to your x and y. So you multiply a into c and just calculate covariance of x, y. So that's what this is. Yeah, we'll just see one example to make this simpler. If you just look at these formula, it will be a bit confusing. Yeah, we could look at an example. And yeah, your correlation coefficient is basically given by this formula. So it's the covariance divided by variance of x into variance of y, the square root of this. So this gives you the correlation. So in R, you calculated like this, cor, I think it's CORR, cor x comma y. So by default, it calculates a coefficient called Pearson's correlation coefficient. So it just tells us how good the linear relationship is. So we can go through these practice questions as well. Okay. So you have your function here, your joint probability function for x and y, and your limits are given here. Your x can range between 0 to infinity, and your y can range between 0 to infinity as well. And let's calculate this for 3 scenarios. So it's just, yeah, you'll be applying different limits here. So let's look at the first one. Yeah, let me just solve with the red pen. So your first one, we're looking at p of x is greater than 0 and y is less than 0. So, not 0, sorry. P of x is greater than 1 and y is less than 1. So here x and y are basically independent. So x has values above 1, y values have values below 1. So these are not related to each other. These are independent. So yeah, in this case, integral, you can do any integral first. Like you could either have dx on in the inside or dy on inside. You'll still get the same answer. So yeah, let's just do it. You write this 2 of e power minus x, e power minus 2y. Let's do dx dy. We are integrating dx first. So the inner limits would be x, the limits of x. So here it says x tends from 0 to infinity. But in this given condition, x starts from 1. So the limits of x would be 1 to infinity. And similarly, y, it tends from 0 to infinity. So lower limit is 0, but y is just less than 0. It stops at 1. So your upper limit here is 1. Okay, we have that. So let's first solve the inner integral now. So inner integral is based on x. So when you do it based on x, this y term will be constant. So you bring 2 is also constant. You keep it outside. So 2 into e power minus 2y is a constant term. And in your inner integral, you have 1 to infinity and e power minus x dx dy. So you first solve this inner thing now. You keep this outer thing as such, 2 e power minus 2y as such. And you have e power minus x. So when you integrate this, you'll get minus e power minus x. So why? Because like we saw that e power, anything that has e power minus ax is equal to minus, what is it? Minus 1 by a e power x. So yeah, I'm just missing that. So, wait. E power minus x. So this is e power minus x basically means e power minus 1x. So this will give you minus, like you'll have e power minus x as such, and you'll have minus 1 in your denominator here. So you'll just get this thing, minus e power minus x. So this you have to integrate over 1 to infinity dy. So e power infinity, wait, let me make it simple. So minus e power minus x is basically minus 1 by e power x. So when you apply this limits here, minus 1 by e power infinity, so minus into minus plus 1 by e power minus 1. Sorry, e power 1. So this is close to 0. So this first term will become 0. And your second term would just be e power minus 1. Right? So you'll have this. Now you just have 0 to 1, 2 e power minus 2y into e power minus 1 dy. Now when you do it in terms of dy, no, it doesn't matter. Like all of these are now in terms of y here. Let's just bring out the constants now. 2 is a constant, e power minus 1 is also a constant, and you have e power minus 2y. So when you integrate this, you'll have minus e power minus 2y divided by 2. So basically you put the minus in front here, and whatever value is here, you put it in the denominator. Oops. And your limits are 0 to 1. And again, when you apply this, you'll have this 2 and 2 get cancelled. You'll have e power minus 1 into, you apply 1 here. So e power minus, sorry, what did I mess up? 0 to 1, e power minus 2. Oh, there's a minus here, sorry. So you'll have minus e power minus 2 minus of, you'll have e power 0, which is 1 minus 1. So basically it becomes plus 1. So e power minus 1, 1 minus e power minus 2. So yeah, this is your final answer here for the first expression. Now, okay, let's just calculate it for the second scenario where p of x is less than y. Oops. We had p of x less than y. Now, how do you do this? You have two limits. You write the expression 2 e power minus x, e power minus 2y, dx, dy. Your limits of x, so x is less than y. We had 0 to infinity in both cases. But since x is less, since x is 0 to infinity, but your x is less than y, the limits of x become 0 to y. And what are your limits of y? Your limits of y still remain 0 to infinity. Yeah. So and let's just, when you solve this, what happens? You keep the outer integral as such. Y terms are all constant. 2 e power minus 2y. Integral of, you keep this. E power minus x would be e power minus x. 2 e power minus 2y, e power minus x, 0 to y, dx, dy. Now we do the same thing, 0 to infinity, 2 e power minus 2y. What will you have now? Minus e power minus x. So you substitute the values. So minus e power minus y, minus of minus e power minus 1. No, sorry, e power minus 0. So e power 0 is 1. So this term becomes plus 1. So it basically becomes 0 to infinity, 2 e power minus 2y into minus e power minus y plus 1 dy. Now all these are in terms of y, so it will be easier. You'll have 2, you just keep 2 out because that is the only constant. 0 to infinity, e power minus 2y, yeah, right. So you'll have minus e power minus 2y minus y is minus 3y, minus 3y. And then plus, so yeah, you just multiply this. You'll have plus e power minus 2y dy. Now you just keep it as such. So minus e power minus 3y, when integrated, it becomes plus here. Like this minus, you again multiply here. So it becomes just e power minus 3y divided by 3, 0 to infinity. 2 is a common term. And secondly, Like when you integrate this, you'll get minus e power minus 2y divided by 2. And limits of this are also 0 to infinity. And when you substitute the values for these, e power infinity is close to 1. No, sorry. E power infinity is close to 0. So 0 minus e power 0 is 1 divided by 3. And then applying this limit, minus e power infinity is 0 again. And then minus e power 0. So minus 1 minus becomes plus. E power 0 is 1 by 2. So we'll have this minus 1 by 3 plus 1 by 2. So 2 into 2 3s are 6 minus 2 plus 3. What is minus 2 plus 3? 2 by 6. So 2 into 1 by 6, 2 by 6 is equal to 1 by 3. So this is the answer for this second scenario. New slide. And the third scenario that was given was P of X less than C. So now, yeah, let's just do the same thing again. 2 e power minus x, e power minus 2y, dx, dy. So limits of x and y are both 0 to infinity. So, but x is less than c. So your limit of x is 0 to c. And your limit of y remains the same. X is not written in terms of y here. There's nothing of y that is specifically mentioned here. So y is still 0 to infinity. And now you integrate it the same way. 0 to infinity. To all the y terms you keep as constant. Inner integral 0 to c. E power minus x dx dy. And then you'll have 0 to infinity. 2 e power minus 2y. E power minus x is minus e power minus x. 0 to c dy. Now you'll have 2 0 to infinity 2 e power minus 2y. You'll have minus e power minus c minus e power minus c plus no, yeah, you'll have plus, because yeah, when you substitute 0 here, you'll have minus into minus e power 0, which is 1. So it becomes plus 1 here. Dy. Now we take all the constants outside. All of these are constants because e power c, it's constant. There's no x, y here. So 2 is a constant. You keep the minus outside. So it becomes e power minus c minus 1. And your integral is 0 to infinity. We have e power minus 2y dy. Minus 2 e power minus c minus 1. You have minus e power minus 2y divided by 2. 0 to infinity. 2 cancel. This minus also becomes plus. So you'll have e power minus c minus 1 into e power minus 2y. 0 to infinity. Now you apply this range. E power infinity is 0 minus minus e power 0, which is 1. So you'll have minus 1. So this term will be minus 1. So just substitute minus here. You'll have minus of e power minus c minus 1 is equal to 1 minus e power minus c. Yeah, so that's it. This is the answer to this. Is that okay? Yeah, just a lot of integration here. Yeah, I'm just looking at the chat box. E power minus x is e power minus x minus 1. Yeah. Yeah, I just got stuck there, but I figured it out. Thank you. And what's next? So yeah, now in this case we have like continuous random variable, and we have to calculate marginal probability and your conditional probability. So this will be quite simple, I guess. So let's first calculate f of x marginal probability. Marginal probability of x, you have to apply limits of y. Now what are the limits of y? 0 to 1. So 0 to 1, x plus y dy. So you can write this as x 0 to 1 dy plus 0 to 1 y dy. So you just have x like y10 plus y square by 2, 0, 1. So when you substitute this, you'll have x into 1 minus 0, which is x, plus y square by 2. So you'll have 1 by 2 minus 0. So 1 by 2. So this is your marginal probability of x. And similarly, marginal probability of y would be y plus 1 by 2. Because it's the same, x plus y, it's symmetrical. Either way, if you do the same thing. The limits are also the same, 0 to 1. You
Ma'am,
calculate the same thing, you still get y plus
ma'am,
1. Yeah.
ma'am, when we integrate for a marginal probability of x, we get instead we are integrating in terms of y, we are
Yeah.
getting the terms in term of x, right?
Yes.
So, ma'am, there is one question which is given in the assignment,
Mm-hmm.
and we have to calculate the marginal probability of x, but all the solution terms are in only y.
Oh,
Terms are
okay.
only in y.
Can you tell me which question that is? Question number? I'll just quickly have a look. And if it's, I'll try to clarify.
Question number 10.
Okay. Yeah, I'm trying to log in. I'll check question number 10. Week 8. Week 8 assignment. Three, four. Marginal densities of X. Hmm.
Ma'am,
Yeah.
I
Yeah.
am the same way all the TAs have suggested, but the answer I am getting is it is not available in the
No.
options. All the terms are in Y. So is it the
Yeah, it's
solution?
probably a mistake with the question. Maybe they meant calculate marginal density of Y.
Hmm.
I think they meant that. Do you get that answer in the options?
No, ma'am, I
Okay.
didn't get that answer.
Mm, yeah, I mean, I'll just let them know. I'll let me have a look at the question as well. Yeah, that's right. You're right.
10th question is not proper. Huh? Excuse me.
Yeah, it looks like it. No, but wait a minute. This is for f of xy. So this is for continuous random variable. Oh yeah, you're right. It's all in terms of y. Yeah, so probably the question is wrong or the options are wrong.
Okay, ma'am, I have tried so many times, but I am getting the same answer. So I just
Yes.
asked you, is this options are incorrect, or
Mhm.
maybe I might be wrong somewhere?
Okay.
Because the
Right,
solution
yeah,
will
I
be in terms
understand.
of only x, no?
It
That's why I'm
has to be in terms of x, but you see in terms of y. To just dominate one instead of x. Yeah. Does or what was somebody else was talking?
That's what, ma'am. 10th question, ma'am.
Yeah, so it's I think the question is wrong or the options are wrong.
okay,
So
ma'am.
because
So we have to select any option, or we just
you
have
can
to
just
skip that.
select, so you select any option anyway, the question will not be graded.
Okay,
Yeah,
okay.
let them know. Yeah.
Thank you, ma'am. Thank you, ma'am. Please proceed.
Okay, madam.
Yep. Okay, where were we? Hmm, what is this? Okay, yeah, we were here, right? From current slide. Yeah, we have calculated marginal probabilities. Now we calculate sorry, conditional probability functions. So x given y, what do? You do the joint probability divided by marginal probability of y. What is the marginal probability of y? Y plus 1 by 2. So this is straightforward. Now similarly for f of y given x plus y divided by marginal probability of x, which is x plus 1 by 2. Done, we got it. And now they've given a different given different limits for x and y. Now you just need to apply those instead of just applying the 0 to 1 and 0 to 1. So yeah, let's apply x limits are 0.5 to 0.8. Y limits are 0.4 to 0.7. And your function is x plus y, dx, dy. Yeah, this should be, you should easily be able to solve this. So you'll have 0.4 to 0.7. Your inner thing can be written as 0.5 to 0.8 x dx plus, and because you're doing it in terms of x, y becomes a constant, 0.5, 0.8 dx dy. What happens now? X square by 2, 0.5 to 0.8 plus y into x 0.5, 0.8 dy. Now, is this fine? Yeah, if you just substitute these answers, you should get the values. You bring 1 by, no, let's not do that. 1 by 2 into, what is 0.8 square minus 0.5 square? Wait, let me. 0.8 square minus 0.5. Oh, 0.39. So if you substitute this, you get 0.39 plus 0.8 minus 0.5 is 0.3. So you'll get 0.3 y dy. Let me take a new page. What did we have? 0.4 to 0.7. think I did a mistake. It's supposed to be here. Okay, so 0.39 divided by 2. So yeah, this can be written as what is 0.39 by 2? 0.39 by 2 is 0.195. 195, 0.4, 0.7 dy less 0.3, you can write it here, y dy. So 0.195 into y 0.4, 0.7 plus 0.3 into y square by 2. So you keep it out, y square. So yeah, this should be straightforward from here. 0.7 minus 0.4 is 0.3 plus 0.3 by 2 is 0.15 into y square. So 0.7 square. 0.7 square is 0.49 minus 0.16. So yeah, you substitute all this, you should get it into 0.3, 0.0585 plus what is 49 minus 0.16, 0.33, 0.0495. So final answer is 0.0495 plus 0.0585. Yeah, 0.108. So this is your final answer. Right. What is happening? I'm not able to share it. Okay, from current. Okay. Okay, the next question here. We have a function x and y are independent. So yeah, your joint property is just f of x into f of y. Okay, to solve this, what do you do?
ಹಿಂಗಿದೆ ನೋಡ್ರಿ ಪ್ರಾಬ್ಲಮ್ಸ್
Sorry?
ಮ್ಯಾಸಚೂಸೆಟ್ಸ್
Yeah.
ಮ್ಯಾಸಚೂಸೆಟ್ಸ್ ಇನ್ಸ್ಟಿಟ್ಯೂಟ್ ಆಫ್ ಟೆಕ್ನಾಲಜಿ ಇದೆ, ವರ್ಲ್ಡ್ ಅಲ್ಲೇ ಪ್ರೀಮಿಯರ್ ಇನ್ಸ್ಟಿಟ್ಯೂಟ್ ಅದು. ಅಮೆರಿಕಾ. ಹೆಂಗಿದೆ ನೋಡಿ ಪ್ರಾಬ್ಲಮ್ ಸೆಟ್. ಲೇಟೆಕ್ಸ್ ಕೇಳಿದಿರಾ ನೀವು? ಇದೆ ಅಲ್ಲ. ಇದೆ ಅಲ್ಲ.
Oh, sorry, I just had to mute somebody. Okay. So yeah, we have this question here. So here, this function, you can see that it's of a specific format. So it's of this format, x e power minus x square dx. So basically it's like 4xy e power minus x square plus y square. So this whole term is equivalent to e power minus x square. And yeah, you have this x here. And 4y, yeah, just have this. So it looks similar to this. So in this case, you have limits a to b. So instead of a to b, what you do is you write this whole expression as e power u. You just simplify e power u and your limits become minus a square to minus b square. So what will you have? So initially you have 0 to infinity. 4xy e power minus x square plus y square dy. So this can, so wait, this is the same as having your, so these terms become constant. Because if you're doing it in terms of dy, all this x term also becomes constant. And wait, you write a half, there's a half here. So you write by 2. And 0 to infinity, 0 square is also 0. Your infinity square is infinity, but you write minus infinity square. So minus infinity. Wait, let's come to that later. Here, we just write it as it is now. E power minus x square, y into e power minus y square dy. 4x e power minus x square. So yeah, now like at this point you have the expression similar to this. Yeah, I was wrong in the beginning. So when you simplify, when you break down this integral, you get an integral of this format. So this is the same as x e power minus x square. You just have y e power minus y square and integral 0 to infinity. So what you do is you write this as 1 by 2 e power u minus a square to b square. So 0 to minus infinity are the limits. To cancel, you will have 2x e power minus x square. So e power of minus u, so e power minus infinity is 0 anyway. Minus of e power 0 is 1. So yeah, you will have minus 2x into e power minus x squared. This is your final answer. You just have to remember this. So yeah, maybe one of our TAs. Yeah, we'll probably put together all these integral equations so that you can remember all these tricks. Like for example, we saw e power minus x. When you integrate that, you'll get minus e power minus x. Yeah, by 1. So, and this thing, like similar things, we'll just put together a document for you to remember so that you can apply this while solving these problems. And your other next problem is calculating a covariance. So basically you have covariance. So the question, yeah, you need to calculate covariance of y, z. Sorry. No. Yeah. What is all the saying? If x, y random variable. Okay, you have to calculate covariance of u and v. So they've given u and v equations. So which is basically covariance of x plus 4y plus 2z, comma 3x minus y minus z. So how can you write this? You construct like pairwise multiplication. Covariance of x, not multiplication, just pairwise terms. So first term of this and first term of this plus covariance of first term of this, comma second term of this plus covariance of first term, comma third term. Similarly, you do it for everything. Did I do something wrong? No. Yeah. X. Yeah. Plus covariance of 4y, comma first term plus covariance of 4y, comma minus y plus covariance of 4y, comma minus z plus covariance of 2z, comma 3x plus covariance of 2z comma minus y plus covariance of 2z comma minus z. Now wait, in the question we have variance of x is equal to 8, variance of y is equal to 12, variance of z is equal to 18. So this is basically covariance of x comma x, covariance of y comma y, covariance of z comma z. So you have these values and you have individual x comma y, x comma z, y comma z values as well. So you just substitute this. Look at this term. So this is basically 3 into covariance of x square. Covariance of x comma x is variance of x. So which is 8. So 3 into 8 plus you have minus here. Covariance of xy is 1. So you get minus 1. And covariance of x and z minus 3. So you already have a minus here. So minus 1 minus plus 3. And covariance 4 3s are 12. And covariance of xy 1. So plus 12. And covariance of 4 into variance of y. So minus 4 into variance of y is 12. So minus 4 into 12, 48. And 4, again you have minus 4 into covariance of yz is 2. Minus 4 2s are 8. Less 2 3s are 6. Covariance of zx is minus 3. So minus 6 3s are 18. And minus 2 zy is 2. Minus 2 2s are minus 4. Plus 2 into covariance of z comma z is 18. So minus 18 into 2, 36. So yeah, you just have to solve all these. 6 8 3s are 24. So if you solve all these, you'll get the answer. Yeah, you can calculate this. Yeah, or maybe I just, no, we don't have enough time.
Ma'am, we are multiply the variance with the constant term.
Yes, exactly. So you just bring whatever the constant terms outside and you multiply the variances. And if there's a minus, you bring that also out and multiply
Yes,
the variance.
ma'am. In third term, like covariance of x comma 2y, then we are multiplying 2 into 8.
Which one?
Yeah, this which you just highlighted,
So this is
covariance
x
of
comma minus z.
minus z. Okay, okay.
Wait,
Then
whatever the third term is. So x comma
third
minus z.
third term you just put
Yeah, so this is this x, this z.
so
1, 2, third term.
so
So you just do covariance of x comma z. It's minus 3. So there's already a minus here. So minus 3 into minus plus 3.
okay, ma'am. 3 you are taking from
Question it's given here.
mu x.
No, covariance of x comma z, right? In the question it's given here. Covariance of x comma z is minus 3.
Okay, okay, okay,
And there's a
got it.
minus here. So you bring the minus out. So basically minus into covariance of x comma z. So minus into minus 3. So plus 3.
Okay.
That's what you've written. Yeah, this looks like a lot of terms. So if you just carefully do one at a time, it should be easy. Okay.
Okay, ma'am. Thank you.
So this is supposed to be with R. I can show you with R. Yeah, these are just two other questions. Similar. You have to calculate marginal density and then conditional density. Now what do we have? So first, marginal density of x. So you have to apply limit of y. Limit of y is 0 to 1. Wait. Marginal density of x is equal to limit of y is 0 to 1, 2 by 3 into x plus 2y dy. What did I do? Okay. So now this x term will become constant. So 2 by 3 x is all constant. 0 to 1 dy plus 2 by 3 2y dy. 2 by 3x y 0 to 1 plus 2 by 3 2y what? Why have I written 2y? What is 2y? So it has to be 4y, right? So this 2 also comes out. So you write 4. So y, oh sorry, there was a 2 here. And 2y, if you integrate it, you'll get 2y square by 2. You cancel it anyway. 0 to 1. And if you substitute this, what do you get? X. Oh, this y is, if you substitute 1, it stays 1. It's 1. Okay, this is right. 2 by 3 into y square minus 0. So yeah, basically 2 by 3 x plus 1. So this is your marginal density of our x. And similarly, you can do marginal density for y. Hmm. Marginal density for y is also 2 by 3 x plus 2y dx. What were the limits of x? Limits of x are also 0 to 1. Now what happens? 2 by 3 x dx 0 to 1 plus 2 by 3 into 2y, which is 4y 0 1 dx. 4 by 3 y x 0 to 1. So what happens here? We have 1 by 3 1 1 minus 0 plus 4 by 3y 1 minus 0. So you basically have 1 by 3 plus 4 by 3y. Yeah, this should be your answer. This can also be 1 by 3 is common here. So you can write 1 plus 4y. Yeah, this is your final answer for marginal property of y. What? Yeah, so you have calculated marginal density for x and y in this question. Now next he calculates the conditional density. So conditional density, basically what you do, marginal probability, like conditional density of x given y. So you have to calculate x given y is equal to but they've given the limit of x. Oh, you have to calculate conditional density of x given y and probability. So yeah, let's first do this. So that's basically this. Conditional f of x given y is equal to y. So what do you do? 2 by 3 x plus 2y divided by marginal density of y. What was it? 1 by 3, 1 plus 4y. So yeah, if you just solve this is basic multiple. Yeah, this is actually the answer for this. And then your next part is you have to substitute these limits. Okay, let me just do this for you. 2x plus 2 2s are 4y divided by 3 divided by 1 plus, no, 1 by 3 plus, no, that's not doing. What am I doing? 1 plus 4y by 3. So these two get cancelled. So 2x plus 4y divided by 1 plus 4y. Yeah, this is your answer to this first part. And next, let's move on to the second part. Now you have to calculate p of x less than equal to 1 by 2, given that y is equal to 1 by 2. So now basically the limits change. So the initial limits were, wait. So you have to calculate x, p of x in given y. So you have to integrate in terms of dx. So what are the limits for x? 0 to 1. But the question now they've specified x is less than 1 by 2, which is half. So 0 to 0.5, like 1 by 2 is 0.5. So it becomes 0 to 0.5. Now your we just calculated your conditional probability here. 2x plus 4y, divided by 1 plus 4y. So y value is also given. Y value is fixed here. So in this expression, instead of y, you substitute 1 by 2. So what did we have? Marginal f of x when y is equal to y was equal to, what was it? 2x plus 4y divided by 1 plus 4y, right? So instead of y, 2x plus 4 by 2. So y is half 1 by 2, right? So 4 into 1 by 2, 4 by 2 divided by 1 plus 4 into 1 by 2, again 4 by 2. So this further becomes 0 to 0 0.5, 2x plus 2 divided by 2 plus 1, 3 dx. And we can bring this 1 by 3 out. You can bring the 2 also out. 2 is also common, right? So it basically becomes 2x plus 2 by 3. It becomes 2 by 3 into x plus 1. So what will happen when integrate x plus 1? X squared by 2 plus x 0 to 0 0.5. No, let us let's bring the 2 inside. So if you, what happens when you bring the 2 in? This stays 1 by 3 and 2 gets cancelled, 2x. So x squared plus 2x. So 1 by 3, 0 0.5 square plus 2 into 0 0.5 minus 0. So 0 0.5 square is 0.25 plus 2 into 0.5, 1 divided by 3, 1.25 divided by 3. Yeah, you either get this or you'll actually, like, instead of keeping it as 0.5, you had kept 0.2. you apply 0.2 here, you would get a fraction. 1/3. Yeah, but still it's the correct answer. The equivalent fraction would be something like 5/12 if you properly calculate it. Yeah, but anyway, this is the whole concept, like how you do it. You calculated your conditional density of X here, and you just substitute whatever value of Y was given here, and you change your X limits according to this, and you do the same integral. You'll get the answer. Okay. Alright. And we had one problem left here. Okay, for this we have to go to R. All right, let me reshare my screen. Stop sharing. Hmm, Studio. No. Mm, Meet gaming. I'll just clean this up. Yeah, please bear with my laptop. It's hanging. Okay. So yeah, in your assignment problem, like I've given two vectors, driver and car. So it basically tells whether the driver is trained or untrained, or was he self-trained, trained by himself. So we just run that. And car, whether the car is big, medium, or small. So now you want to make a contingency table. So these are two variables. So driver is X, car is Y, or whatever, either way. And if you want to do a contingency table, how do you do it? You just do table bracket driver comma car. So this gives the absolute numbers. So as you can see, this is called a contingency table. You see each category for X, self, trained, untrained, and each category of the car, big, medium, and small. And these are the number of car. Like these are the numbers. Like 25, like 25 drivers who self-drive, they have a big car. Like they can drive big car. It could be interpreted something like that. And 33 people self-drive and have a medium car. 34 people self-drive and have a small car. And 18 people are trained, have a big car. And yeah, similar ways. So this gives you the absolute numbers. And now you want to calculate the relative frequency. So what is relative frequency? Basically, this number divided by the total number, right? So for that, what do? You just do this table divided by the total number of observations. So table of driver comma car divided by length of driver. So these two vectors, they have the same length. So it's basically driver means number of people. So yeah, divided by total number of people. If you do it, you'll get your absolute frequency. So this basically means 12.5% of the people self-drive and have a big car. And 6.5 people are trained and have a small car. So this is how you read it. And now you want to add the marginal probabilities. Now what do you want to do? You do this function. So all this was discussed in your videos, in your lecture videos as well. So those were much detailed. Yeah, so I'm just showing you how these look like. So add margins of table driver comma car. So this will just add a extra column to your this thing. It's basically the sum. So 25 plus 33 plus 34, 92. So it sums up each row, and here it sums up the each column. And this sum is 200. This sum will also be 200. And now when you want to calculate the percentage people, what do? We do this. So we have like 100% people, 46% of the people self-drive, and um sorry. So this is the marginal probability. So marginal probability of the self-driving people is 46%. So this is in percentage. Wait. If I want to, in terms of probability, I just don't multiply by 100. So yeah, 0.46 is the marginal probability of the self-driving people. So you just sum up all the y terms and you get this. So now what do you do if they ask for what is the probability of trained people given they have a small car? So what will you do? So this is the joint probability of trained and having a small car, right? Trained and small car is this. So this is your joint probability. Joint probability divided by small. What is the marginal probability for small? 0.33. Divided by 0.33. This is your answer. This is the joint probability. Sorry, this is the conditional probability for probability of a train driver given he has a small car. So you do joint probability divided by marginal probability. Yep. Is that clear?
Yes, ma'am.
Yeah, cool. And similarly, I could just show you about correlation. So empty cars is basically a data frame that is inbuilt in R. So it's just inbuilt. Like any of you, if you just type empty cars, MTCARS, it'll give you this data frame. So this basically has different cars, different brands of cars, right? Ferrari, Porsche, and like all these different Mercedes, all these types of cars. So this is one variable X. And oh, sorry, we are looking at now what we're doing, we're looking at covariance and correlation. So we have cars and we have different variables. I think these
Madam,
are all
excuse me,
the
madam.
engine
Madam,
parameters.
excuse me.
So yeah,
Madam,
sorry. Yeah.
madam. Madam, in the assignment questions, like one table is given like for patients and dosage, and
Wait, just a second. Your voice is a bit low.
madam, in the assignment we are given a question based on R, like the patients and dosage is given
Okay.
a data set, and in that like child, elder, and young also is there, and they're asking some percentages, like how many persons are there who are
Yeah.
child. So how to
Yes.
calculate this one, madam? How to, and one more question, how many patients are given medium dosages?
Exactly.
So this kind of how to
Yeah. So that's what
procedures
I
of
was
answering
just
and all.
showing. So if you want percentage, you do this. You basically do add margins, table of X comma Y divided by total number of people, or it's just length of any of these variables into 100. If you do this, you'll get a table that looks like this. So this basically tells you the percentage of people. So these are the percentage of self-drive people having big cars. Yeah. So that's how you read it. So all these numbers are joint probabilities. And these numbers are marginal probabilities. Like my percentages, sorry. Yeah.
And questions like how many child and elder patients were given small dosages?
Yeah, so what
Child
do you
and
do? You just add up.
okay.
small dosage, let's say you have elder, young, let's say elder, child. Okay, elder, child, small. You just add up the small, 17 plus 6. You do something like that.
And some statements are given like which of the following statements is correct?
Mm-hmm.
Uh,
Wait,
like number of elder patients given the
let me have a look at your question.
7th and 8th, madam.
7 and 8. 2, 3, 4, 5, 6, 7, 8. Which of the following number of elder patients given the medium dosage is the
Hmm.
same as number of elder patients given the large dosage?
How to conclude this? Like,
You have to like calculate and see. Wait, let me see if I cannot do that. 7. I'll just give you an idea. Patients. So this basically gives you numbers. Number of patients who are child given a large dosage. And yeah,
yes.
that's what was your question again? 7 and 8. Which of the following statements is correct? So let's first look at the first statement. Number of elder patients given medium dosage. So what is that? Number of elder patients given medium dosage is 22, right?
Yeah.
And is the same as number of elder patients given large dosage. So remember we had 22. And now look at elder patients given large dosage. It's 21. It's not the same.
Okay.
So yeah, that statement would be false. So that's how you have to look at the data.
Okay.
Yeah.
And for 8th question, madam, like
What do we
asking
have? Wait, which of the following statements is similar? Number of elder patients who are given small dosage.
more than the number of
Wait, number of patients given small dosage. Number of patients given small dosage. So it would be all these patients. So we do this. So the sum under small. So this would be all the patients who are given small dosage, right?
Okay.
Number of patients given small dosage 73. So this is more than number of young patients who are given large and medium dosage. Number of young patients given large and medium. Number of young patients given large and medium. So 16 and 16, if you add these up, you don't get. So this is still smaller than 73. So that's how you just compare the terms.
Okay.
Yep. Okay. Yeah, we were looking, yeah, now this is done. We were talking about correlation, covariance, all that now. So we're looking at this empty cars data set from R. It has different cars and several variables here. So I think these are all car specifications. I don't know what these are, like some, any of you know this? I don't know, some gear value, QSEC, HP. I think these are just some engine specifications. So anyway, we have this data. We want to see if some values are correlated. Right? What is disp? We want to compare this disp parameter and HP parameter. We want to see if these are correlated across all the cars. So what do you do? So if you want to do covariance, you just do COV, the two terms. I don't know what, yeah. No, this is basic. Yeah, let's just see correlation. So you get a 0.7 correlation coefficient. So 0.7 is almost close to linear. So it's almost dispersion and HP are correlated in all these cars. So all cars, they follow a similar trend. and plot. Mhm. Share something. Okay, I'm trying to plot this.
Madam, what
Wow.
does the dollar symbol stands for, madam? In the
Okay, dollar is basically my laptop was, yeah, just give it a few seconds. So, like if you remember the data frame, we had multiple columns, right? The name of the data frame is empty cars.
yes.
If you put dollar, it will show all the columns that are present in the data frame. See, you can see all these columns: cycle, SIL, DISP, HP, DRAT. So you see all the column names. And now you just want to compare these two columns. You want to compare DISP column and HP column. So how do you do? Empty cars of DISP, comma, empty cars, dollar, HP. So you are just telling R to consider only that specific column. So instead of having it as a vector, you can do one more thing also. So this is the longer way. You can just put disp as a vector. So this would be empty cars of DISP. Now if you look at this, it looks like a vector, right? It looks like what you had here. Like in your question, it was given like the elder children mid dosage. So that was a vector. So that can also be given to you like an Excel file. So if they give it to you as an Excel file, how will it look like? Oh, yeah, let me reshare my screen. So if they had given you like that, patient, dosage, elder, large, elder, small, elder, medium. So yeah, this would be a data frame. If your data is given to you as a file and you read the file, it will be like this. In that case, what do? You have to specify your data frame like DF, whatever you read it, DF column patient and DF column dosage. So yeah, it's just like you're telling R which values to take. So that's what the dollar means. You're telling it to take this column from this data frame. So it's considering it as a vector. So you need vectors to input here, right? So X is a vector, Y is a vector. Yep, that's it. Yes, anyway, if you try to plot this relationship, you get something like this. So as you can see, as X increases, as this increases, HP also is increasing. So almost a linear correlation. So that's why you got some value 0.7. 0.7. Yeah, so that's what it tells you. Okay, we had one question. Let us look at that. My laptop is the value of, I think I've got a different question. Age and time. Do I have that data?
Yes, ma'am. Data is provided in the assignment.
Okay, let me check. Yeah, I'm just trying to show you something, but my computer is hanging. Okay, so let me show you one more data set. So I'm just loading it from here. So I have a file. So I'm just reading the file. So the data was given to me as an Excel file. I am reading the file like this. Read CSV, specify the path to the data. I think I should just close some apps. It was hanging. Or square. Okay, let's look at the data. It looks like this. You have some age category and you have taste. Now, what was that question? X denotes age. Wait, I don't know if I'm looking at the. Okay, anyway. Ah. Okay, let's like stick to this empty car. Empty cars. So let's say we calculated the correlation between disp and HP. And now you want to calculate covariance between disp and HP. So you just do covariance disp comma HP. Oh, sorry. Empty cars. Empty cars. So you get this value. But like we saw in theory, R gives us covariance where the denominator is n minus 1. So if you have to achieve the covariance based on this expression, what you have to do is the value that you got with R, you have to just multiply by total number of observations. So basically length of LENGTH, length of like all the number of rows. So you could be anything. Length of disk, it's all the same. Length of disk will be equal to length of HP also. So you have to do, no, I'll show you a better way. LENGTH. Length of, so it has 32 rows, right? So your N is 32. So you want to calculate covariance for 1 by 32 observations divided by 32 observations. But R gives you for like all the summation of all these divided by 31. So what will you do? You have to do covariance of HP into n minus 1 divided by n. So n minus 1 is 31 divided by n is 32. So this is your actual covariance answer. So yeah, well, let me see if you have any problem of that sort in your question. Yeah, so you have question number 13 in your assignment. So when you do this with R, you have to multiply by n minus 1 divided by n to get your answer. So you have to choose this answer in your options and not this.
So here we have to find out the length of this.
Yeah. So in your question, you have petrol and distance. So you just have to find length of this petrol, basically.
Okay.
Yeah,
Okay.
have to do this. That's it. That's one thing. And do you understand why that you're doing that, right? Because of this. It's
Yes,
1 by
ma'am. Yes,
n.
ma'am.
Yeah, that's it. Yeah. So that's all for today's lecture.
And ma'am, from the next question for correlation part, uh, I think it is 14. Same, we can do this from the R,
Yes.
correlation coefficient.
Yeah. So correlation coefficient will always be between -1 and 1.
So what is the command, madam, for that?
You just have to do COR. Wait, I showed you somewhere. Yeah, it has to be like this. COR.
So see, we have to write this COR and our data.
Yeah. So in this case, you need petrol and distance. So
Okay.
you just, yeah. So both these are vectors, I believe. Or how was the data given?
Yes, vector.
Yeah, so your vectors are given. So you just have to do like core petrol comma distance. That should give
Okay,
you.
ma'am.
Yeah.
Thank you.
Welcome. Yep, that's it. If you have any questions, you can post it on the discussion forum as well. I believe. Wait. So yeah, if you log into your portal, you'll have this Q&A. It'll ask you to be redirected. You click continue.
Ma'am, only 10th question of this assignment
Yeah.
give the value of a margin of x,
Margin X, right.
margin and value of y.
Yeah.
And in this question, we have.
Yeah. One of you can just post it here as well, and I can also just coordinate.
Okay,
Yes.
ma'am, I'm just
Yeah.
the same.
So any such problems you have, you can just put it here. Like click new conversation, you write
Okay,
your
okay.
problem and you post it here. Like everyone will be able to see it. If you do this, your supervisor, like professor will see, and the TS who are setting the questions could also see it. Yeah.
Okay, ma'am.
They'll be mindful next time. Yeah. There's no more questions. We can end the class. I'm sorry. Yeah, it it's already late.
Madam,
Sorry.
this recorded video will be available by
Yes.
tomorrow
Yeah,
morning,
tomorrow morning when you wake up.
8 o'clock.
Yeah.
No problem. Thank you.
Okay, ma'am. Thank you, ma'am.
All right. Thank you. Thank you all. See you.